Part C, role of data structures and optimality of algorithms. So you can see we will learn two topics. C.1, the first topic, role of data structures. Let's look at a simple problem. Problem number 2 of this class, search an unordered array. So let me give you the problem first. Given an unordered array. So here, this unordered property. Important, yeah. And array we represent in this way. The indices from 0 through n-1, total n elements. Yeah. And a search key k, the k value to be searched. So which element has the same value as the given key? So we want to find that item. Yeah. Find an index I such that k equals a of I. So very simple example, right? Yeah. But here, although the problem is very simple, but we want to learn several basic things. Yeah. First, the problem type. So this is the search type. In this class, we will learn 3 basic types of problems, algorithm problems. Search type, search, sort, second type. And the third one, selection type. Our next problem, we will learn the selection problem. Yeah. All right, so the data structure, just a simple array. Yeah. For this one, I give you the reference in our textbook, section 2.1, page 47. Yeah. All right. Now, let's look at this question. Why the data structures are important in algorithm design? Yeah. First, let's look at this question from abstract high level. Yeah. The answer is, through data structures, we can make our data well organized. Yeah. Sometimes we need to organize our data in a special way. Yeah. Yeah. And so that the algorithms can take advantage of the structure and get a better performance. Yeah. So here you can see the structures of the data important. Sometimes, especially when problems are very complicated, to organize data and put some special structures in it, it will be very important. Yeah. Yeah. So later when we'll learn more and more complicated problems, so we will get better and better understanding on this topic. All right, so for this one, our data structure very important. Very simple. Yeah, just array, very simple. Yeah. And our operation, basic operation, comparison. So we only need to use comparison to find the key to be searched for. Okay? Yeah. How do we do the comparison? Yeah. Very simple. Compare k and one element in the array, a of I. When we start with I value equals 0, yeah. Initial condition. Yeah. But when we do the comparison, basically we have 2 cases we need to consider. The first case, k equals a of I. In this case, we find the key to be searched for, yeah, and return index I location. Yeah. Return the location I. So, all right. And the second case, k not equal to a of I. Yeah. Yeah, the first one. After we return index I, the program terminates. So we can do the next thing. All right, but for the second case, k not equal to a of I, then we need to do further iterations. Okay, yeah. So the next round, we compare k with a element at index I plus 1, the next one in the array. Yeah. So we'll keep doing things like this. Yeah. But sometimes when you compare the next element, you may not have the next element, right? Because if I already is the last element, n minus 1, you don't have another element, okay? In this case, because we couldn't find any element that matches the given key. So in that situation, we just return -1 index. So this one actually is used as a flag, right? Yeah, denote something special. Because the normal index cannot be negative, right? The normal index from 0 through n minus 1. So we use some special number that cannot be the normal index number to denote some special case. No element can be found in the array to match the given key. This special case. Yeah. So in this, after that, then the program terminates. So we complete the whole processing. Yeah. So that's the whole procedure. Yeah. Pretty simple, pretty straightforward. Yeah. But we need to try to learn something in this very simple example. Yeah. All right, so first, this algorithm, so what we are doing here, yeah, we have a name for it. We call it sequential search or linear search. Sometimes people also call linear search, sequential search. Yeah. Same thing. Yeah. All right. But the next thing we want to ask, the question we want to ask, how do we measure its performance? How fast it is? We want to measure its performance. Yeah. So let's do this important work. Yeah. All right, so now to measure the performance. Yeah. So what do we need to do? Yeah. All right. To do, we need to count the number of comparisons. Counting. Yeah. Do counting. Yeah. So you can see counting is the basic technique we need in this class when we do the performance analysis. Sometimes we also call efficiency analysis. So we need to do a lot of counting. Yeah. All right. So here I use a simple table. Yeah. Under each column corresponds to one array element. So that is, if the given key equals that particular element, how many comparisons do we need to find a match? Yeah. So very simple. Yeah. The first element, one comparison. Okay. Yeah. After the first comparison, you will know if the given key equals the first element, and so on. The second one, 2 comparisons. Okay. And the last element, n comparisons. After that, there is another case, no match case. Still, you need n comparisons for that no match case. All right. So after that, we want to summarize a little bit. Yeah. Some basic facts. First, we know comparison 1, the first element that matches the given key, that's the best case. The smallest number of comparisons we need to use, 1. So that's the best case. Yeah. Then the other end, n number of comparisons containing 2 possibilities. Yeah. Worst case. You need a maximum number of comparisons to get that case. Yeah. All right. So now the question, how to measure overall efficiency? So here I want to ask you overall efficiency. Yeah? Yeah. Not a particular case, the overall case. Yeah. Here, the answer. If you want to give the answer, you cannot use the best case because the best case cannot represent the overall case. Yeah. And you cannot use the worst case. The worst case cannot represent the overall case, right? Yeah. So the best one for the overall case. Yeah. You need to consider all the cases in a fair way, in a reasonable way. Yeah. So what's that? Yeah. All right. So we need to get a little more information about all the cases. Yeah. Sometimes we may not have enough information. So here to answer this question, we may need a little more information. Yeah. So here we need to make some reasonable assumptions here. Yeah. All right, so let's look at what kind of assumptions we need to make here. Yeah. So for all these possible cases, so we can make reasonable assumptions like this. Yeah. First, all right, so assume for all these cases, so we do not look at the no match case. We look at the matching cases and matching subcases. Yeah, matching cases. Yeah. So we can assume all these matching cases have the same probability. That's reasonable, right? Yeah. Because no information related to this part given, so we can make that reasonable assumption. Yeah. All right. So that's the first one. Yeah. Second, then for no match case, we cannot assume it has the same probability with any of the matching cases. We cannot. So we need to introduce another assumption. All right, so related to the probability. Okay, so let's do this. Yeah. So for the index case, yeah, the function returns an index. So that's one of the matching cases. Yeah. We assume the probability is P. Yeah. For all matching cases combined together, the probability is that P. This P value between 0 and 1 inclusive. All right, so that's a reasonable assumption. Yeah. Then the last case, no match case, the -1 case, the function returns is -1. So its probability is the complement part of the P. So 1 minus P. Yeah. So that's our second assumption. Okay. So with this second assumption, now we are ready to measure overall efficiency. Now we have enough information to get the overall efficiency. Yeah. All right. So the next step, we will do analysis under these assumptions and get an answer for that overall efficiency. All right. So we will do that in our next video, C.2. Yeah. So all right, let me stop C.1 first.